So we were talking about in our last video how we were going to work out the relation between the potential difference across a capacitor and the charge on it by creating a circuit in which we were able to have a constant current flowing. So let's see how we do that. Well, what we do is we use a variable resistor, basically, which we constantly adjust to keep our microammeter reading constant. So this would be a microammeter here, or just an ammeter. Here we'd have our voltmeter. Here we'd have a capacitor. This is our variable resistor. This is our cell. Just to point out, if you're confused at all about any of these circuit symbols, or etc., just how we were doing this, I'd recommend to go back to the AS section and look at our circuit diagrams, etc. videos again, because we covered all of this here. So this is our variable resistor. What we do is we're going to be able to basically, we'll measure the current through the variable resistor, and we'll just adjust the resistance so that we get a constant current flowing all the time. So we can call that current I here. And so we've got a potential difference here across our set of epsilon. All that's going to happen is that the potential difference across this this capacitor here is steadily going to increase. We'll call it V. So this potential difference is going to increase, and we'll monitor that with our voltmeter. We'll know the current flowing in the circuit because we've made it constant, and then we'll be able to know the charge on the capacitor just by using this formula here, Q equals IT. So from that, we'll be able to work out what plus Q is, the charge, we'll be able to work out what the Q is, which is the charge stored on our capacitor, just by using that formula there. Doing that, we can basically plot a graph. We can just measure this plenty of times. But here's the really nice thing, is that we're measuring the PD across the capacitor, like I was saying. We measure the PD across the capacitor. But then what we do is we don't need to plot, we can remove time from the equation completely, because we've got our charge at every moment in time, and we've got our potential difference at every moment in time, so we can just plot a graph of our charge against our potential difference and ignore time entirely. So therefore, we then have a graph of charge against potential difference, and then it didn't really matter how we came up with these results. It didn't matter whether this was a constant current circuit or not, because the relationship between charge and potential difference is always the same. This is why this always works. This is a trick, because this circuit allows us to do this really easily, but there's nothing special about this circuit in the way that the relation between the charge and the potential difference. That's the nice thing. So what do we find? Well, we find that the charge stored in the capacitor is directly proportional to potential difference across it, which is really nice. What you basically find is that when you have zero potential difference across your plates, you have zero charge on them. And then from there, you just scale up proportionally. So we'll get this kind of nice graph here. So we basically have our charge in coulombs here. Remember, that's our unit of charge. Potential difference in volts. And we see that just as we increase our potential difference, we see the charge is proportional to it. So you see our charge is proportional to our potential difference.
Hey guys. To continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.